So up to this point, we have been able to integrate a very, very limited set of integrands. We've been able to integrate polynomials. We have been able to integrate very simple trigonometric functions. We have been able to integrate very simple exponential functions and very, very simple rational functions. We have been able to integrate those. Now, what we're going to do today is we're going to introduce a technique called substitution that will dramatically increase the number of integrands that we're able to actually integrate and find the antiderivative. And later on in the course, we will be introducing a much larger set of techniques to help us to integrate an even greater library of functions. Now, this method that we're introducing today, which is called Method of Substitution, is very useful if you're integrating something like this function. When do you use method of substitution? You use it generally in the following case. You use it when your integrand seems to contain a function, some function, let's just call it u equals g of x, and the derivative of g of x, let's call it du dx, equals g prime of x. Now here's what I mean by that. Let's look at this particular integrand. I'm seeing something very interesting here. I'm seeing the appearance of x squared in this integrand, and I am also seeing an appearance of the derivative of x squared, namely 2x. And in that situation, this is a prime candidate to use substitution, where g of x, the original function, is x squared, and g prime of x appears, 2x appears as well in the front. Now here is the process by which we use method of substitution to integrate that function. We will nickname by u this function g of x that we have noticed, that g of x and g prime of x appear in our integrand. Now, using this equation in step 1, next step is to calculate du dx, to calculate g of x. Now let's get a little running example here, a running example to apply to the function 2x e to the x squared dx. In our running example, the u is the x squared that has appeared, and du dx is equal to the 2x which appeared in front. Now, step 3 of the substitution process. Take this equation du dx equals g prime, or in our case equals 2x. And your next job is to isolate dx. And the key idea here is to treat du dx as if it were a real honest-to-goodness fraction with a numerator called du and a denominator called dx. So solve for dx. So I can multiply by dx to clear the fraction. I can divide by 1 over 2x, and I get 1 over 2x du is equal to dx. Solve the equation for dx. Now here's the real beautiful trick. Having established the identity of dx and of u here, the goal is to go back into your original problem and replace everything so that it is in terms of u instead of being in terms of x. Replace all x's so that they are in terms of u's. So what does this mean? This means that the first thing that I'm going to replace is this x squared. I'm going to replace x squared because I know that x squared is equal to u. and I would prefer to write it in terms of u. So I will replace not e to the x squared, but e to the u. I will also replace this dx that has appeared. I will replace dx with what I know to be equal to 1 over 2x du. Now you have chosen the correct u value. You have chosen the correct g of x. If at this end of this process you are able to get rid of absolutely every instance of x, and now you have just an integral that contains the letter u only. So I am integrating e to the u, dummy variable u, with respect to u. So now that we have set up this much nicer, cleaner equation, we can integrate the function. We can integrate the function that we wrote in terms of u. Integrate the integrand with respect to u. So the integral of e to the u with respect to u is e to the u again, plus some unknown arbitrary constant, because this is an indefinite integral. And then for the final answer, all that we have to do is go back and replace u with the g of x function again. We used u temporarily to make the integrand simpler. Now in our final answer, let's go ahead and go back and replace u's with x's again. So in my running example, I would instead write e to the x squared plus c for the final answer. And you can check and you can confirm that e to the x squared plus c is the antiderivative of 2x e to the x squared. If you take the derivative of e to the x squared, chain rule will cause that 2x to appear in the front. And that's what this substitution method is based on. It's based on using chain rule in reverse, undoing chain rule, to integrate functions that might have come from using chain rule. Let's try another example just to get the idea cemented in our minds. Suppose that we tried to integrate 5x squared cosine x cubed dx. Now what's interesting to me about this is that this function has an x squared appear. So if I call u equals x cubed, then du dx would be equal to 3x squared. Now, I don't exactly have a 3x squared appearing in the rest of my problem, but I do have a 5x squared, which is very, very close to 3x squared. So let's suppose that I went ahead with this u substitution, and I just tried it out to see if it will get me an integrand that I can actually work with. 1 over 3x squared du is equal to dx, solve for dx, and let's integrate 5x squared cosine of what is now u instead of x cubed, and we can replace dx with 1 over 3x squared du. Now, x squareds cancel each other out, and what I need to integrate is 5/3 cosine u du. Unfortunately, this is simple enough that I am able to integrate it with respect to u, and I will get 5/3 sine u plus c. Is this my final answer? Not quite. To get the final answer, I need to eliminate u and put x's back into this function. So for the final answer, I would use 5/3 sine x cubed plus c. And you can go back and you can check. If you take the derivative of this function, you will surely get the original 5x x squared cosine x cubed as the result because of chain rule. Now, just a friendly warning, as you're going about these problems, sometimes there is a trial and error process. Sometimes you pick a u value which you think will work out just fine. You go and you plug it in and you do the substitution, and when all is said and done, you get an integrand which is still not possible. So don't worry about it. Trial and error is perfectly acceptable in Calc 2. If your first choice of u doesn't work out, then go back and try a different u and try again.